Welcome all. So, we will be starting our lectures. So, last time we looked into the examples. So, today we will continue with the examples and look into how to design the energy absorbers. Okay. So, in this particular example, we have been given an energy absorber in a railway buffer system. Okay. So, this buffer system can be made. Okay. It can lie in the nose of the railway vehicle, or it can be in the form of the stoppers, okay, that we normally see in case of any yards. Okay. So, the characteristics of this energy absorber is as such: the maximum reaction force is 120 kilonewton, the average reaction force is 90 kilonewton, and the stroke is 0.4 meters. Okay. It means that the displacement from the point of impact, okay, is 0.4 meter. Okay. The value of R max, okay, the value of R max is 120 kilonewton, and the value of average reaction force, okay, that is the integration over the entire area, okay, of R x, okay, averaged over the entire stroke length is 90 kilonewton. Okay. So, these are the given energies. Okay. It is being asked that the impact wagon has a mass of 5 tons and approaches at 1.6 meter per second. So, we have to compute the fluctuation factor. Okay. So, the impacting wagon has a mass of 5 tons and approaches at a velocity of 1.6 meter per second. Okay. So, the impactor has, this guy has a mass of 5 tons, okay, and it is moving at a velocity of 1.6 meter per second. So, to give a perspective, the 5 tons can be taken as two heavy cars. Okay. So, each car normally weighs around approximately around 2 tons. Okay. So, keeping on the higher side, so this impacting wagon has an equivalent mass of 2 impacting cars. Okay. And it has a velocity, and it has an approach velocity of around 6 kilometer per second. Okay. It means that it is lying in the yard and it is approaching the yard. Okay. And the energy absorber has this characteristics. Okay. So, we need to compute the fluctuating factor. Okay. So, we will go one by one. So, fluctuating factor. Okay. So, fluctuating factor, we have seen fluctuating factor is nothing but the ratio of R max to R naught minus 1. Okay. So, R max is given by the maximum reaction force absorbed by the energy absorbing system is 120 kilonewton, and the average reaction force given by this equation is 90 kilonewton, okay, minus 1. Okay. So, it comes down to 0.33%. It means that this number gives a sense of fluctuation between what is happening in the maximum reaction force and the average reaction force. Okay. So, let us say that the maximum reaction force and average reaction force are equal. It means that the fluctuation factor will be 0. It means that there is no fluctuation or there is no disparity between the maximum reaction force and the average reaction force. Okay. The energy absorbed by the system is given by the average reaction force times the stroke length. Okay. So, average reaction force is 90 kilonewton. So, E absorbed is given by the reaction force times the stroke length, okay, and this comes out to be 336 kilojoule. Okay. The energy in the wagon, okay, that is simply the kinetic energy of the system given by half mv square. So, energy in the wagon. Okay. So, the impacting wagon gun is moving at a mass of 5 ton. So, this becomes the mass and it has a velocity of this one. So, half mv square. Okay. So, the energy in the wagon is 6400 joules. Okay. So, we have computed the fluctuating factor, that is 0.33, estimated the energy absorbed by the absorber. So, energy absorbed by the absorber is 36 kilojoule, and check if the absorber can safely absorb the wagon's kinetic energy. Okay. So, we need to compare the wagon's kinetic energy, okay, wagon's kinetic energy versus the energy absorbed by the absorber. Okay. So, Wagon's kinetic energy comes down to 6400 joules and energy absorbed by the system energy absorber comes out to be 36,000 joules. Okay. So, energy absorbed by the energy absorber is significantly higher than the kinetic energy of the absorber. Okay. So, check if the absorber can safely absorb the Wagon's kinetic energy. Yes, interpret the safety margin. Okay. So, the safety margin can be defined in any number of ways. So, here we are defining the safety margin as the energy absorber capacity, okay, energy given, energy absorbing capacity divided by the impacting energy. Okay. So, the energy absorbing capacity is 36,000 joules and the required energy absorption capacity is 6400 joules. Okay. So, the energy margin comes out to be, this ratio comes out to be 5.6. Okay. It means that the energy absorption capacity is 5.6 times greater than the required. Okay. So, here the system is safe, as well as since this ratio, okay, this ratio is 5.6 times, okay, nearly 5.5 times. So, the system we can say it is over designed also. Okay. Even if this ratio was greater than 1 or 1.1, okay, you could have safely said that the energy absorbed by the absorber can safely absorb the energy given by the impactor. Okay. So, our system is safe, as well as it has a higher energy absorption capacity than the requirement that is given out here. Okay. So, moving ahead, we will look into another example. Okay. Here the energy absorber has an original length of 1.5 meter. Okay. So, the original length of the energy absorber L, okay, let us say this is my energy absorbing system. So, the original length is 1.5 meter. Okay. We can make it this as a column, okay, an axial energy absorbing system. So, it has a length of 1.5 meters, okay, and the maximum deformation of 0.9 meters. Okay. So, it has a maximum deformation of 0.9 meters. Okay. So, we can say delta equals to 0.9 meters. Okay. The residual or the permanent deformation is 0.2 meter after rebound. Okay. After the system rebounds from this thing, okay, the permanent deformation that this system can have is 0.2 meters. Okay. So, maximum deformation is 0.9 meters, okay, and the residual or the permanent deformation is 0.2 meter after the rebound. Okay. The reaction force during loading is 5000 Newton. Okay. It means that the R naught is 5000 Newtons. Okay. So, we need to calculate the stroke efficiency. We need to calculate the stroke efficiency. We need to determine the energy, total energy absorbed in the system, and we need to compare what is the elastic rebound energy. Okay. So, the estimated energy from the recovered 0.7 meter. So, this 0.7 is coming from 0.9 is the maximum deformation, okay, and 0.2 is the permanent deformation. Okay. So, the recovered deformation is 0.7 meters. Okay. So, strain in the system, okay, strain is defined as the total displacement over the entire length. Okay. So, this is definition of axial strain. So, the average axial strain is defined by x max divided by L. So, 0.9 was the total deformation and 1.5 was the length. So, the strain is 0.6. Okay. So, after that we are calculating the absorbed energy. So, absorbed energy is given by R naught times x max. Okay. So, this comes out to be 4500 joule. Okay. So, the elastic energy, of the system is 5000 times the total deformation minus the permanent deformation. Okay. So, the 0.7 is the elastic deformation. Okay. So, this comes out to be 3500 joule. Okay. So, here we can comment about the energy absorbed. So, the total energy, okay, was 4500. Okay. Out of this 4500, 0.9 was the deformation in the system. The system deformed to a limit of 0.9. Okay. So, when it happened, okay, the energy absorbed was 4500 joule. Okay. After this deformation, what happened was 0.2 meter was the permanent deformation and 0.7 was the recovered deformation. Okay. So, out of this 4500, 3500 joule was recovered, okay, and only 1000 joule was permanently absorbed. Okay. So, here 1000 joule irreversibly dissipated, rest is the rebound energy. Okay. So, interpretation, so here we can say that out of this 4500 joule, only 1000 joule was given as the total dissipated energy. So, here our interpretation can be that the system has a low damping. Okay. So, system is rebounding a lot. Okay. So, we can say that 3500 over 4500, okay, this much percent, around 60 to 70%, okay, is being recovered, okay, and approximately only 30% is being absorbed, okay, even less than 30% is being absorbed. Okay. So, the total energy absorption capacity of the system is low as compared to the conventional energy absorption system, okay, and the system is rebounding a lot. Okay. So, it is a inefficient energy absorption system. Okay. Okay. Moving ahead, next example, and the next example we see an industrial robotic arm requires an emergency stopper that absorbs kinetic energy during a fault. Okay. So, this is, you can say, this is sort of a robotic arm applied to any structure, okay, and the requirement is that it requires an emergency stopper. Okay. Some sort of emergency stopper will be required. Okay. So, even if there is a breakdown in the system, it is able to hold this robotic arm during any malfunction or during any fault or during any breakdown. Okay. So, the arm of the robotic mass is around 80 kgs. Okay. So, it has a mass of 80 kg and the movement velocity of this system is around 1.2 meter per second. Okay. So, this is the kinetic energy of the impactor. Okay. So, this is the signature of the impactor. Okay. And when it hits the stopper is compressed by 0.12 meter. Okay. So, this is the signature of the energy absorber and this is the stroke of the absorber. Okay. So, x equals to 0.12 meters. So, the volume of the stopper is 0.004 cubic meter and the mass of the stopper is 1.6 kgs. Okay. So, this stopper, okay, okay, it has a mass of 1.6 kgs and the volume is 0.004 cubic meter. Okay. So, this is the signature of the energy absorber. So, we need to compute the kinetic energy of the robotic arm. So, the kinetic energy of the robotic arm is given by half mv square. So, mass is 80 kgs, velocity was 1.2 meter per second. So, it becomes 1.2 meter per second and the total energy comes out to be 57.6 joules. Okay. So, this is the demand imposed by the system. Okay. Then what we need to do? We need to design a system. Okay. We need to design the energy absorber such that this whole demand is being met. Okay. So, the energy absorber is able to absorb the 57.6 joules of energy, okay, which is imparted by the impactor. Okay. So, this demand quantity now becomes my capacity, which is the requirement which has to fulfilled by the energy absorber. Okay. So, this becomes my total energy requirement divided by my stroke length. The stroke length is given by 0.12 meter because this is the amount by which the stopper compresses. Okay. So, the average reaction energy is 480 Newton. So, we have computed the kinetic energy of the robotic arm, we have determined the average force required to stop it over 0.12 meter. Okay. So, the average force is R naught, okay, and E requirement is R naught times x. So, E requirement comes from the demand imposed by the impactor, okay. X is known. So, we can calculate our average reaction force. Okay. So, the average reaction force is 480 Newton. Okay. After that, we are asked to calculate the energy density and the specific energy. Okay. Specific energy and the energy density we have seen earlier. So, specific energy and the energy density. Okay. So, specific energy has to do with the total energy per unit mass, and energy density has to do with the total energy per unit volume. Okay. So, the total energy requirement was 57.6 joule. Okay. So, when it is divided by the volumetric constraint 0.004 cubic meter, this gives our energy requirement per unit volume, and when it is divided by my total mass, the total energy requirement, this gives my energy requirement per unit mass. So, specific energy and the energy density is being calculated. Okay. So, given the data, we are able to calculate the requirements of our energy absorber. Okay. So, moving ahead. So, in the next example, we see a spacecraft lander. Okay. The signature of the spacecraft lander is as such. So, it has a compressible damper. Okay. So, if you say our spacecraft is something like this, and these are the landing gears. Okay. So, this is the landing length. So, here a compressible damper is being put. Okay. This can be an magnetorheological damper, electrorheological damper, or any other fluidic type of damping system. Okay. So, it can be made of any type of fluidic type of damping system. Okay. So, it is being tested. Okay. So, during simulation touchdown, its stroke was 0.5 meter. Okay. So, the stroke of this system is x equals to 0.25 meters. Okay. So, this is the signature of the damper. Okay. So, the average reaction force of this damper is 3200 Newton. Okay. So, R naught is 3200 Newton. Okay. And it has a elastic recovery of 0.1 meter. Okay. So, x elastic is 0.1 meter. Okay. The volume of the absorber is 0.003 cubic meter. The volume is 0.003 cubic meter, and its mass is 0.8 kg. Okay. So, this V, this M, x elastic, x recovery, R naught, these are all the signature of the energy absorber. Okay. So, we are talking about the energy absorber. Okay. So, calculate the total absorbed energy. Okay. So, the absorbed energy is simple, we just give it as a product of the average reaction force times the total stroke. Okay. So, the total stroke is 0.25 meters times the R naught, it becomes 800 joules. Okay. So, this we can simply do. So, after that, the estimate the stored elastic energy. So, here we know that energy in an absorber is constituted of two parts. Okay. One is the energy dissipated and other is the energy stored. Okay. So, energy stored is in terms of the recovery, and its recovery is 0.1 meters. Okay. So, this will be given by this quantity. Okay. So, 0.1 meter is recovered, and out of 0.25 meters, 0.15 meter is dissipated. Okay. And after that, determine the damping factor. So, for calculating the damping factor, we need the energy dissipation. Okay. So, we can calculate it both ways. Okay. Energy absorbed by the damper is E dissipated plus E stored. E dissipated is 800 joules. Okay. E stored is 320 joules. So, E dissipated becomes 480 joules. Okay. Or we can go the other way also, we can calculate E total, which we have calculated as R naught times X total as 800 joules. Okay. E stored equals to R naught times X stored, this becomes 320 joule, and energy dissipated is R naught times X which is not recovered. So, this is 0.25 minus 0.1 which is 480 joules. Okay. So, both the term will give the same answer. Okay. So, after that we have to determine the damping factor. So, the damping factor alpha is E dissipated divided by E total. Our E dissipated is 480 divided by 800. Okay. So, the damping factor comes out to be 0.6, which gives an average type of damper. Okay. So, its value is slightly more than 0.5. So, it has a moderate damping. Okay. So, what is the significance of 0.5? Okay. So, 0.5 is the middle path. Okay. If it is 0.5, it means half of the system, half of the energy by this energy absorber is being dissipated and the other half is being stored. Okay. So, if this value is more than 0.5, okay, it means that the efficiency of the energy absorber is increasing, and if the value of the stored one goes down, it means the energy absorber is an efficient one. Okay. If the value of the stored energy is more than 0.5, it means that most of the energy is being recovered. Okay. So, this is not a efficient system. Okay. So, normally the alpha should be greater than at least 0.5, okay, in order to be considered as a moderately, even a moderately damping system. Okay. Moving ahead. So, we now look into the next example. Okay. So, here a rear underridge guard is put on a truck and is tested for crash energy absorption. Okay. So, this we can absorb as some sort of a guarding system or a plate fin type of system. Okay. So, it is compressed by 0.2 meters under an average load of 20 kilonewton. Okay. So, R naught equals to 20 kilonewton. Okay. So, this is the signature of the energy absorber. Okay. The structure weighs 1.2 kg and it occupies 0.1 meter cube. Okay. So, the mass of the structure is 12 kgs, okay, and the volume it is occupying is 0.01 cubic meter. Okay. Okay. And it is compressed by 0.2 meter. So, x, so the stroke length is 0.2 meter. Okay. So, the energy absorbed. So, the energy absorbed is given by R naught times x, that is the reaction force absorbed by the energy absorber and the dissipated stroke. Okay. So, the total stroke is 0.2 meter. So, the energy absorbed is given by this equation, okay, R naught times x. So, it comes out to be 4000 joules. Okay. So, determine the energy density and the specific energy, again same thing, energy per unit volume and energy per unit mass. So, we know the total energy in both the cases, that is same, divided by the total volume and total mass. Okay. So, in case of per unit volume, this is 4000 divided by volume is 0.1 cubic meter, and in the other case 4000 divided by 12 kgs. Okay. So, we calculate the specific energy and the energy density. Okay. Now, we compare it with the some standard requirements. So, standard requirement, okay, according to some specification, it gives that energy per unit mass should be greater than 1500 joule per kg and energy per unit volume should be greater than 10 raised to the power 5 joules per cubic meter. Okay. So, we are asked to see whether our this particular energy absorption, okay, the underride guard does it meet these requirements. Okay. So, here we looked into the per unit mass criteria. So, criteria is that it should be greater than 1500, our is only 333 joules. Okay. Okay. And for the requirement of, so here it is requirement of 4 into 10 to the power 6. Okay. So, here it is meeting the requirement. So, here it is not meeting the requirement, here it is meeting the requirement. Okay. It means that the volume is okay, but we have to lower the mass. Okay. So, it fails in the specific energy criteria, okay, per unit mass criteria it is failing. So, it means that we have to use a lighter material with same volume. Okay. So, the volumetric criteria it is meeting, but the mass criteria it is losing out. Okay. So, if we use the same material, okay, if you use a material with the same volume, but with lower mass, okay, meaning a material having less density, then this criteria might be met. Okay. So, suggest changes to improve compliance if needed. So, the suggestion is use a lighter material, okay, a material having less density. Okay. So, moving ahead. So, now we have finished the one part. So, we have finished the general principles for design of energy absorbing structures. Okay. So, now we will be moving to selection of energy absorbing materials. Okay. So, I will stop here and will continue in the next phase. Thank you.